Hi guys, let's keep talking about Atwoods machine. So remember we said that an Atwoods machine is where we have two unequal masses that are attached by some type of rope and then a pulley system. So in an Atwoods machine, we're going to pretend like the pulley system here is negligible. So let's pretend like the pulley, even though it's there, it really doesn't exist in my Atwoods. So they asked me, determine the magnitude of the acceleration of the two objects and then the tension that's going to be in the string. So first of all, I need to think about the acceleration, what's the magnitude of it, but then also tension. So when I'm thinking about this as an overall system, I want to separate both of these objects, and I want to do it for one reason, and that's because it's easier for me to think about forces acting on mass 1, and then also what are the forces that are acting on mass 2. But is their acceleration the same? And you should be saying yes, and that's because they're attached. So M1 is going to be accelerating in the same way that M2 is, it's just that they're moving in, ultimately M1's acceleration is directed upward, but M2's acceleration is going to be directed downward. And I can account for that whenever we do our sum of the forces. So let's do this problem and determine its acceleration, okay? So it's a terrible drawing, but it's okay. M1 is up, M2 is going down. So let's do M1 first. Free body diagram for M1. Since it's accelerating upward, I have tension that's going to go in the positive Y. And then I also have the weight force of M1, so then that's going to go down. I'm going to call that M1G because I want to make sure that I am specifying which one is mass 1 and which one is mass 2. So let's write a sum of the forces in the Y direction for this first object mass 1. Since it's accelerating upward, there's my acceleration vector. It should be T minus M1G. And that should not be equal to 0 because we are accelerating upward. It should be equal to M1 times A. Okay, let me simplify this down then. T equals, T minus M1G equals M1A. So this is true for my first mass. And then let's just make it even simpler and say T equals M1A plus M1G. Okay, let's stick with that, but then let's also do the exact same thing for mass 2. Okay, so for mass 2, I have tension, I have weight force. Since it's accelerating downward now, mg should be larger than tension. Let's write the sum of the forces in the y here. I have mg should be first, it would be positive since its acceleration is going in the same direction as that particular vector. So we'll do mg minus t equals, and you know what, let's be more specific, m2g minus t is equal to m2 times a. Okay, so m2g minus t equals m2a. So on that one, let's kind of rearrange that one too, so then that way it looks better. So what? On that one I would have t equals m2g minus m2a. Okay, so I know that the tension for mass 2 is this. I know that the tension for mass 1 was here. Their tension should be equal because they're connected together. So if I know that tension equals this for mass 1 and tension equals this for mass 2, how about I just set them equal to each other? So M1, so tension here is M1A plus M1G. So M1A plus M1G equals the tension here, M2G minus M2A. Why did I do that again? I did that because their accelerations are the same and the tension on either side of them should also be the same because they're connected. They're a system overall. So this is what I'm left with. Let's simplify this down. Let's see if I can make something better from this. And actually, I'm going to do this on a different page. M1A plus M1G equals M2G minus M2A. Okay, if I simplify this, let's actually just get A's on both sides and then let's get the G's on both sides. Because my goal is to find acceleration. So if I do that, let's add M2A over here. So I have M1A plus M2A equals M2G minus M1G. Okay, so I'm left with that. And then let me just separate out A here. So A times M1 plus M2 is equal to G times M2 minus M1. I want A all by itself, so if I do that, let's divide both sides by M1 plus M2. So now I'm left with A equals G times M2 minus M1 over M1 plus M2. And this is my acceleration for an Atwoods machine. So this is my answer that I want. Okay, my last question on that part was to determine the tension in the lightweight string. You pretty much already did that. We did that on the last slide when we said tension is going to be equal to M2G minus M2A. So I would go here, and then I would just plug in what we solved here for A. So I would plug this in to A right here, and then you could end it at that. That would have been totally sufficient. So if we plug in what we found here, let's go back, plug this in to A, you could have left that as your equation then and you would be good. Okay, so that's an Atwoods machine, and we're going to do tons of practice on that too. Let's go to another one. This is an Atwoods machine, but now it's an Atwoods machine on steroids because it's on a ramp, on an incline. And we love to do this problem because it makes it a lot more difficult. So it says a ball of mass M1 and a block of mass M2 are attached by a lightweight cord that passes over a frictionless pulley of negligible mass. The block lies on a frictionless incline, so no friction, we are on Earth, children, and yeah, no air resistance. The block lies on a frictionless incline. Find the magnitude of the acceleration of the two objects. So we just said they're attached, they're a system, so they have to be accelerating in the same way. Their magnitude of acceleration should be the same. So let's do this one. Okay, so the incline looks like this. There's my pulley, and then the ball is this way, and the ramp was this way. We're going to call the ball M1, and we'll call the block M2, okay? And this one is accelerating this way. That's accelerating that way. So there's my picture. My goal is to find acceleration. So same thing that we do every single time. Separate these up. Free body for M1, sum of the forces. Free body for M2, sum of the forces. Let's go. M1. Tension, weight force. Tension should be larger than the weight force because it's moving upwards. Let me actually change that. Okay, much better. So my sum of the forces for this first one, sum of the forces in the Y is going to equal tension minus M1G equals M1A. Okay, let's do T equals M1A plus M1G. Okay, so by now I'm hoping that we've done enough of these that you know free body, sum of the forces. Let's set that equal to something. Okay, so that's my first tab, but now I need to do M2. Okay, M2's free body is going to look a little bit different, yes? Because now I have this incline that's also working on this system, or working on this block. So because of that, here's the normal. Weight force is straight down, and then tension is going to be at a 90 degree to the normal force. So here's tension. Okay, we're going to do all of your favorite things and skew the axes. Right, Rachel?
Skew the axes!
Woo! Okay, so now that I have done that, I want to say which one is my x, which one is my y. Here's my y. Tension will be along the x. It's moving this way, so it should make sense then that this is going to be my x-axis. Okay? We're going to break up then the weight into components. We're going to break up the weight into components. So here's theta. So there's my forces. That's my free body. My question then, which forces are causing the acceleration? Forces in the y, forces in the x. If it's accelerating this way, according to my picture. You should be saying the forces in the x. Yes? I hope we all see that. Okay, so forces in the x. I have tension, and then I also have this x component here to the weight force. So instead of some of the forces in the y like we did for M1, I'm going to do the sum of the forces in the x. And that's going to be equal to mg, but it's a component, and the x component is the sine of that, so mg sine theta. And then tension is going in the opposite way in which acceleration or the block is moving, so we're going to do mg sine theta minus t. Let me be more specific. M2 g sine theta minus t is equal to M2a. I have an acceleration there. That's what's equal to that net force. So, what do I do now? Well, I already know what t is equal to. I found that up here from Mass 1. T is equal to M1a plus M1g. Let's plug that in here. And then that way I can try to move everything around then and solve for A. So I have M2g sine theta minus M1a plus M1g equals M2a. Okay, but now let me make this a little easier. So minus M1a minus M1g equals M2a. Okay, so now all I need to do is simplify this. Let's get the a's on one side, and then let's get everything that has a g on one side. So we'll have M2g sine theta minus M1g equals M2a plus M1a. Okay, now, just like we did on the last one, let me shrink all of this, guys. Okay, just like we did on the last one, we can do, let's take out the g. So then this becomes M2 sine theta minus M1 equals A times M2 plus M1. Let's divide both sides then by M2 plus M1, and that will leave me with the acceleration. So here's M2 plus M1, boom. There's my acceleration. Okay, so the only difference then between the Atwoods machine acceleration where there's not then that angle or theta is just that component then of that particular mass. Okay, let's move on to friction. I think we are. Nope, just kidding. Let's do conceptual first. All right. This is a block of mass M rests on the floor of an elevator that is moving upward at constant speed. What is the relationship between the force due to gravity and the normal force on the block? So of these options, write one down. We'll talk about it at the beginning of class tomorrow. Guys, I don't know if I even said this or not yet. I'm switching the schedule around a little bit. I wanted to do a lab tomorrow, but instead, I think I want to do some practice with this, with some of these problems, just while it's kind of like fresh in our minds. So we're going to play a game tomorrow, doing some practice with this, and then depending on your own preferences, we could do the lab on Wednesday, or we could wait until Thursday. It's just up to you. We can talk about that tomorrow, but tomorrow we're definitely going to do some practice with this. So, block of mass M rests on the floor of an elevator, moving upward at a constant speed. What's the relationship between force due to gravity and normal force? It's A, the normal is greater than the weight force. B, the normal is equal to the weight force. C, the normal is less than the weight force, but it's not zero. D, the normal force equals 0. Or E, it just depends on the size of the elevator. Okay, so answer that one for me and have an answer, and then we'll go from there. Oh, wait, I think I just missed one. I did. Okay, well, we'll skip that one. Guys, friction. If we wanted to define friction, how would we do that? Okay, so when an object, yes. When an object is in motion on a surface or through a viscous medium, there's going to be a resistance in motion. So the force of friction is a force that is always going to oppose the direction of motion, or of the direction that the motion would be in if in the absence of friction. So there's a few different reasons as to why we are going to see friction, and I think I'll get in that in the next slide. Okay, so friction is just going to be when an object is in motion on some type of surface or through some viscous medium, and friction is the resistance to motion. It's the force that is resisting motion. Some of you want to call that inertia. I saw this misconception on some of your quizzes. Inertia is not a force. Friction is a force that resists motion. Inertia is not a force that resists motion. Inertia is just a natural tendency for an object due to its mass, but it is not a force. So friction is that force that you are thinking of when you think of inertia, okay? So let's make sure that we get that kind of clear. The only reason that we walk is because of friction. If we didn't have friction, or if friction wasn't here, we wouldn't be able to even walk. So for example, let's look at this. Let's look at Carol. Let's assume this is Carol. So Carol is trying to walk here, and she clearly can. She's not falling all over the place, even though, she did say YOLO in the lab. So her force of her foot is directed backward, but friction, that resistance to motion, what's making her not slip, is going to be directed then the forward X direction. So it's the frictional force exerted on the foot by the ground that allows her to stand up and continue to move. Because her force is exerted, she's exerting her foot then on the ground. The ground has to exert something back up on her, and that's going to be a frictional force. So why do we have friction? We thought at one time it was due to surface irregularities. That's what we thought. We thought that surfaces just weren't maybe as clean cut, and they had really sharp, jagged edges, which really isn't completely wrong. It's because of these surface irregularities that friction is due to adhesion. I have something called local adhesion, meaning that I have whatever two surfaces are in contact with one another, and they are temporarily stuck together at that moment. And that's what's causing friction. It's like this little temporary bond that occurs, and because of that little temporary bond, I have to overcome that, and that's what friction is trying to do. So friction is trying to overcome these little local adhesions, and it does that with every surface. Even if you think a surface is super smooth, it's not the smoothest. It's actually probably really rough if you look at it microscopically. So this local adhesion is what causes friction. We have a couple different types of friction. We have static friction, kinetic friction, and rolling friction. And we usually think about these between solids, because if we think about liquids or specifically like gases or in air, then it's a different type of resistive force. So we're talking about static friction, kinetic friction, and rolling friction. We're really specifying that it's between two solids. So static friction is when the frictional force is large enough to prevent motion. I cannot move an object because the local adhesion is too great to move it. Kinetic friction is when two surfaces are going to slide along one another. I broke the local adhesion. Ultimately, it's just the surfaces that have those surface irregularities, and it's trying to temporarily adhere, the surfaces are, but it's sliding along so I'm not able to have that local adhesion the way that I would in static friction. So static friction, frictional force where it's at rest or it prevents motion. Kinetic friction, when two surfaces are sliding along one another, we're in motion. And then rolling friction, we're not going to focus on rolling friction in this chapter. We're actually going to focus on that in like chapter 11. And ultimately, that's just when an object is going to be rolling without slipping. So rolling without slipping could be like a basketball rolling around on the gym floor. If we want to calculate friction, the frictional force is proportional to the normal force. So friction, and specifically you see here this is S, so this is representing that it's static. So static friction is going to be proportional to mu sub S. That mu is called the coefficient of static friction. So if it's mu sub S, it's static friction. If it's mu sub K, it's going to be the coefficient of kinetic friction. So friction is proportional to normal force. Friction is proportional to normal force. Okay, let's say that we're talking about an object that is definitely in static friction. Then static friction, it should be greater than mu times the normal. Let's say that I want to determine what's the maximum value of frictional force, or what's the maximum value of force that I need to apply to an object to get it to move. How can I overcome friction? So static friction at its maximum is going to be when it is equal to the coefficient of static friction times the normal. That's going to depend on physical circumstances. So it depends on what the objects are, so on and so forth. And then kinetic friction, same thing. The only difference is that for kinetic friction, it's when mu k is equal, or when mu k times the normal is going to be equal to my kinetic friction. Mu k, coefficient of kinetic friction, is usually way smaller than the coefficient of static. And I want you to think why. If something's already moving, it's not going to take a lot of extra force for me to keep it moving. Versus if something is at rest and I want it to get moving, it's going to take a lot more force to overcome all of those local adhesions to get that object to go into motion. Okay, so on this question, it says a box of weight 100 newtons is at rest on a floor where mu s is equal to 0.4. A rope is attached to the box and pulled horizontally with tension is equal to 30 newtons. Which way does the box move? A, it moves to the left. B, it moves to the right. C, it moves up. D, it moves down. Or E, the box does not move. So try this one. There's a little picture here. There's my mass. It's on a surface. The coefficient of static friction is 0.4. Tension, they told you, was 30 newtons. What are my options? We'll look at our hands tomorrow. Okay, this question. A box sits on a flat board. You lift one end of the board, making an angle with the floor. As you increase the angle, the box will eventually begin to slide down. But why? Why does it eventually slide down? Is it A, because the component of the gravity force parallel to the plane increased? B, coefficient of static friction decreased? C, the normal force exerted by the board decreased? Is it D, both 1 and 3, which should say A and C? Oh my gosh. both A and C, or E is all of them. A, B, and C. Okay, so then tell me that one. We'll do that on our little hands tomorrow. All right, what we just talked about too, this figure illustrates what happens as the applied force increases. First, we have a static frictional force, and then we see that kinetic frictional force is going to take over. So right now, Carol is trying to push this filing cabinet. Oh, Carol, why are you doing this all by yourself? Okay. Huh?
She's blind.
She clearly has no idea. So Carol is trying to push the filing cabinet. She's not strong enough. So she alone doesn't have enough force to overcome how this filing cabinet is locally adhered to the carpet or the surface. And let's say now Matt comes along to try to help Carol, okay? So Matt's like, oh, Carol, what are you doing? Let me try to help you. So Matt applies more force with Carol to try to move it, and ultimately they're going to reach that threshold. They're going to reach the maximum amount of static friction that this particular filing cabinet can have when it's on the floor. So if I'm graphing this, that force that I'm applying versus static friction, I'm going to reach this threshold, and then I'm going to get it moving. Once I get it moving, that force is going to be here. I'm going to keep it moving at some plateaued level that I'll see with kinetic friction, okay? Table 4.1 in your book has, actually no, this is not in your book, this is from a different book, but that's okay. You're fine, you're fine. So the coefficients of friction depend on the materials that are involved. So I see that this is just friction between different materials. There's aluminum on aluminum, glass on glass, rubber on concrete. So this is the static coefficient of friction, and then this is the kinetic coefficient of friction. You can see that roughly the static are a lot larger than the kinetic, and that should make sense because it takes a lot more force. So I'm going to see these coefficients as just being larger because of that. Okay, I'm going to stop here. We're going to do some practice with all of the other stuff with like Atwoods machines and then Atwoods machines on inclines, things like that tomorrow in class. We'll play a game. And then Wednesday we can do some stuff. If you like what we do tomorrow, then depending on tomorrow we can do that again on Wednesday, or we could do an Atwoods machine lab. I don't know which one will be better, but we'll look. Okay, please make sure that you are prepared for anything that may come your way tomorrow, like as you walk into class with an index card. All right, goodbye, children.